New users often install Linux for the promise of total control over their operating system, but without a deep understanding of the underlying system architecture, that control quickly collapses into catastrophic system crashes. The dilemma starts with expectations. We approach Linux expecting the built-in guardrails, hidden folders, and confirmation prompts that standard consumer operating systems use to protect us from our own mistakes. Linux does not operate this way. The system assumes you are an expert. If you issue a self-destructive command, the system will execute it exactly as written, without asking. This flowchart maps the typical beginner lifecycle. A user installs the OS, searches online for a goal, blindly copies a command from a forum, and triggers an error. To bypass that error, they force the command using root, the highest administrative account, resulting in immediate system corruption. Look closely at this specific junction. By copying and pasting a command, the user bypasses any logical understanding of what the code actually does. Without foundational knowledge of the system's architecture, this sequence leaves no barrier between a simple typo and a total system collapse. To avoid this cycle, we need to conduct an ROI analysis on the Linux learning curve. We have to identify exactly which technical skills require an upfront time investment to yield a stable system. You face a direct trade-off: the immediate convenience of executing commands blindly against the high friction of learning how the operating system actually functions. Transitioning to Linux requires a shift in user responsibility. You are trading consumer safety nets for direct control, and that control demands a significant initial cognitive investment. This chart weighs learning friction against system stability, with ease of implementation on the vertical axis and stability on the horizontal. We place our first pillar, command verification, right here, contrasting verified understanding against blind execution. The initial input cost here is high. Instead of scraping commands from internet forums, you must pause and parse technical documentation, known as manual pages, to decipher exactly what specific flags and arguments are doing. This drastically slows down your ability to execute immediate tasks. It introduces severe workflow friction, because you are reading syntax instead of getting the job done. But the trade-off is absolute clarity. Accepting this slower workflow entirely eliminates the risk of executing obfuscated code that could wipe your hard drive or corrupt your personal data. Looking back at the chart, we map our second pillar, permission architecture, in the high-effort, high-impact zone. The required input is dense. You must memorize how Linux handles user and group hierarchies, based on structural concepts of read, write, and execute permissions. Investing time to map out these structures eliminates the dangerous guesswork behind recurring permission-denied errors. You know exactly who has access to what and why. Securing your files properly using this hierarchy prevents severe system vulnerability. It locks down critical data and stops unauthorized access at the structural level. Bypassing these initial learning hurdles to save a few minutes creates an illusion of speed. In reality, you are secretly building a highly fragile environment ready to break under pressure. Operating with root access grants you absolute power over the entire machine. Because the system obeys root without question, any minor operational error is immediately magnified into a systemic failure. Returning to our chart, we plot a third node, root discipline. This represents the principle of least privilege, requiring a standard user account for daily tasks. This adds friction, demanding secondary authorizations and passwords for basic administrative changes. This friction acts as a critical sandbox. It isolates inevitable beginner mistakes to a single user profile, protecting the core operating system from global destruction. Finally, we plot our fourth pillar on the chart, file system navigation. This requires severe mental input. You have to entirely abandon the consumer logic of a main C drive and invest the time to memorize a unified directory hierarchy. You must map out the specific core architecture, differentiating etc for configuration files, var for variable data logs, and home for user files. Possessing this mental map drastically reduces your diagnostic time when the system eventually fails. You know exactly where to look for the logs and the configuration rules. Without this architectural knowledge, navigating a broken system blindly is physically impossible. You will be stuck wandering through directories with no context for how they connect. Structural friction, such as restricted user access and complex file hierarchies, functions as a vital systemic defense mechanism. Theoretical proficiency in these concepts is useless without consistent, hands-on terminal practice. You have to apply these rules in isolated, safe environments. This comparison matrix divides users into two operational camps across the 4 pillars. For the tactical user, requirements are pragmatic. You can skip file system mapping, but skipping root discipline exposes data to accidental keystrokes. The strategic user, however, must fully adopt all 4 pillars. The strategic user must actively analyze raw error logs to understand why a failure occurred, instead of immediately seeking out pre-packaged workarounds online. The trade-off is steep. You will endure extreme cognitive fatigue in the early stages, but that friction is the only mechanism that builds actual, autonomous administrative resilience. The painful process of diagnosing and solving complex system errors is exactly what forges true, unbreakable capability. Achieving Linux competence requires a deep respect for the system's architecture and a sustained investment in its foundational principles.